Alright, so today we're going to be solving a problem called unique paths 2, and the reason why I chose 2 is because there's actually a first edition of this problem that's just called unique paths, but unique paths 2 just takes the original idea and adds a different thing to it, so if you can solve this, you can solve the first one. So basically in this problem we're given an M by N grid, and we start in the top left corner, and there's some obstacles in the way, and our goal is to get to the bottom right hand side, so this star right here, and we basically have to find out how many unique paths that there is between the start and the end, and we can only move right and down, so those are the restrictions. So when you look at a problem like this, and it's a 2D grid, and you can only move right and down, you have to think, what could this be? What type of problem could this be? And I'm going to give you the answer. It's DP, so we're going to be using DP to solve this, because normally if you can move any direction, like left, right, down, left, up, all the different directions, it would be a backtracking problem, or maybe a DFS problem or something like that. But because they restrict it like that, you can kind of use that as an indicator that will lead you in the direction of thinking that this might be a DP problem. So anyways, if we go ahead and go over to a little whiteboard here, we can see that we've got the dude up here and the end down there. So the first thing that we're going to need to do to solve this problem is make a DP array, which is pretty common. And the DP array here is actually kind of intuitive because it's 2D and the original matrix that they give us is also 2D. So basically we have to think about something which is our base case, right? Like DP problems, they always need some sort of a base case. And so in order to find out our base case, let's consider something. If we only move down or we only move right, we have found one path, right? Because if we just go down, down, or right, right, because we can only go down and we can only go right, this whole column here is going to be 1, because we are only going one path. We can only go down to get to this cell, and we can only go right to get to this cell. And the same thing is for this cell, and for this cell, and for this cell right here. This cell, we just don't go anywhere, so it's just one path, and we just don't move. But if we go either to the right or down, that's one path, because we're only going one direction. And this is kind of a combinatorics problem, if you think about it, because in order to find the rest of these cells, what we actually need to do is sum up these two cells. And the reason for that is because, well, in order to get to these two cells, it's one path. But if we were to get to the cell that's kind of in between, we would just sum up these two ways, right? So like, for example, this would be 2, which makes sense because we could go right and then down, or we could go down and then right. So it's just taking the diagonals and summing them up. However, with this problem, we're given an additional thing that we need to watch out for. And as said before, there's an obstacle in the middle cell. So you might think, what's the simplest thing to do in order to account for these obstacles? And when I was solving this problem, I thought, well, let's just go through, and if there's an obstacle, let's just set it equal to 0. And turns out that's actually the correct solution. And if we go through here and add up the rest of these, right here, this would be 1. This would also be 1 by adding up the one that's in the previous column in the previous row. and then you would add up these two here to get 2. So 2 would be our final answer for this grid that they give us in the example. But there is another case that we need to watch out for. Okay, so if there is an obstacle in one of the cells that would be considered a base case, then we have to consider what would happen after that cell, because basically we can still fill in 1s here for all the cells that don't have an obstacle. However, if there is an X here, then we would still put 0, but we have to remember that everything after that would also be a 0, because if you look here, you can see that if we've met a wall here, there's no way that we can get to this cell, because this entire column onwards is completely blocked off. We have to go down, because remember, we can only go left and we can only go down. So our only option here is to go down. So with that being said, if there is an obstacle, all of the cells that come after that obstacle would have to be 0. So we can do the rest of this grid by filling it out, having 1 here, 1 there, 2, and then 3. And well, does this make sense? Well, let's see. We can go like that, and I'll change colors as well. We can go like this, or we can go like this. So yeah, 3 different paths, and that checks out. Okay, so how would the code for this work? Well, the first thing that we will have to do is create the DP array. So you can do this pretty easy in C++ by doing it like this. And also something that we should have is our row and column sizes. And so you can get the column and the row sizes by doing that. And I'm just going to save those as a variable. So the next thing that we want to do is fill out the base cases. And as talked about before, basically we are going to go through and we'll do the rows first. So but remember, we have to watch out for something, and that's these the case where we have an obstacle in one of the outside in one of these first columns or rows, right? So in order to account for that, let's just create a Boolean variable. And we'll say if obstacle grid at this index is not equal to 1, because obstacles are marked with a 1, then we can set our DP equal to 1. Else we'll set it equal to 0. And we'll also add the condition that our Boolean must be false as well. And then also down here we can put if the obstacle grid is equal to if it is equal to 1, then we need to set our Boolean to true, so it knows to fill the rest of the grid with the zeros. All right, cool. And then we can do the exact same thing except for the columns, right? So we just switch these here. and we're all set. So that should work. And we also need to reset our Boolean variable. And then after that, we can go through and we can start at 1 for both the row and the column. And we can say if the obstacle grid at the same index is not equal to 1, if it's not an obstacle, then we can fill it with the previous row and the previous column sum, the sum of those two elements. So we can say the DP array at this index is equal to DPI minus 1 j plus DPI j minus 1. Else, so if it is an obstacle in the original matrix, then what we do is we just know that it's going to be 0. We can't go there. And then once we're done, we can go ahead and return R minus 1, C minus 1. And yeah, let's try it out. Okay, that works. Let's try both test cases to be sure. Okay, seems good. Let's submit. See how it works out for us. Okay, cool. So, as you can see, this specific approach is not optimized, but I feel like this way makes the most sense. And it does run faster than 63.5%, even though the runtime is a little bit unreliable on LeetCode. But yeah, overall, this is a pretty easy problem, and I will be doing more. So thank you for watching.